Hey guys, today we're in section 5.6, rational functions. We're going to be going through what rational functions are in this video, and in the next video we're going to go through an example of how to graph one using all the stuff that we've learned, being very thorough about it. So what are rational functions? Well, rational functions are essentially a quotient, which means division, of two polynomials. So if h of x is a rational function, if h of x is equal to f of x divided by g of x, where f of x and g of x are polynomials. And so it's been a few sections since we've talked about polynomials, but just remember that polynomials are x to some power plus x to some other power, right? We have leading coefficients, we have leading terms, and we have degrees of polynomials. So make sure that you remember your definition so you can follow along with this lecture. So as an example, if f of x is x squared plus 4 and g of x is x cubed plus 27, we let h of x equal to f of x over g of x. Is h of x a polynomial? No, it's not, right? Because polynomials do not have quotients, right? We can't have division in a polynomial. But is h of x a rational function? And the answer is indeed yes, because both f of x and g of x are polynomials, and it's a quotient of polynomials, and that's how we recognize rational functions. So you may be asking yourself at this point, since rational functions are made up of polynomials, then how do rational functions differ from polynomials? Well, recall that polynomials are smooth, continuous curves. The smooth part talks about us being able to the smooth part talks about not having any jagged edges or corners in the graph of the function. And the continuous curves part, talks about the fact that we can draw a polynomial from beginning to end without picking up our pencil. And if you look over to the right, to the rationals, you'll see that we've lost the continuous part of our characteristic. So rationals are just smooth curves, which means that they may not necessarily be continuous. Okay, so how do they differ? Well, for a polynomial function, we know that all polynomials have domain all real numbers, right? And so that's because of the continuous part of our characteristic. And rational functions now, because they are made up of two polynomials being divided by one another, then the domain of a rational function is dictated by what's happening on the bottom. Because recall that because a rational function is essentially a fraction, we can never divide by 0. And because we can never divide by 0, that means that if g of x is ever equal to 0, then it's going to cause problems for us when we try to graph or evaluate our rational function. So our domain is always going to be limited by x such that g of x is equal to 0. So our domain is always going to be limited by this. And so actually let me say that in a more intelligent manner. But the idea is the same. Our domain for a rational function is going to be the set x such that g of x does not equal to 0, right? And so because we never want our denominator to be 0 because we can't divide by 0, we can't use any x's that make the denominator 0. And we've talked about end behavior of polynomials, but typically, depending on which polynomial we're talking about, the end behavior as x approaches positive or negative infinity, y, right, our range, is always going to be positive or negative infinity as well. However, with rationals, this is not always the case. It is the case sometimes, but not always. So we actually have three different cases for determining the end behavior of rational functions. And we'll talk about those in a second. So first, let's talk about a few new definitions. First definition is horizontal asymptote. And essentially, a horizontal asymptote is a value that a function follows as x approaches positive and negative infinity. And so a horizontal asymptote really is just another way of describing end behavior. Our second definition is vertical asymptote. And a vertical asymptote is a value that a function never can approach. And so, not that it can approach it, but a value that a function never crosses. And so a horizontal asymptote visually will be represented by a bunch of dashed lines that go on forever. And a vertical asymptote, as the name suggests, is a dashed line that the function can never cross. And so it's really these vertical asymptotes that remove the continuous part of the characteristic that we gain by being just a polynomial. So polynomials don't have horizontal or vertical asymptotes, but rational functions actually have both. And so vertical asymptotes give us two different discontinuity types. So we have a discontinuity type that's called removable and a discontinuity type that's called an unremovable discontinuity. And so just a quick example of this, you'll cover this more in calculus, but if f of x is equal to x minus 2 over x plus 2 divided by x minus 2, you'll see that because we have factors that are common, we can eliminate, right? We can cancel out these two values and we'll be just left with x plus 2. However, because f of x was originally x minus 2 times x plus 2 over x minus 2, we have to abide by the restrictions of our original function, not the function that we ended up with after doing some algebra. And so f of x, the domain of f of x, is all real numbers except x such that x cannot equal positive 2, right? So the domain of f of x is it can't be 2. And so because this is the original domain, it affects the graph when we try to draw it. And so you'll notice that f of x equals x minus 2 times x plus 2 over x minus 2 has a hole at the value x equals 2, right? And you'll notice that here I've drawn the graph of just what x plus 2 would look like, right? It's just a line. It's y equals mx plus b. And so a line is continuous. It doesn't have any holes. And so this is what this picture would look like. And so they're basically almost the same graph, but if you are given f of x in this manner, you have to respect the domain restriction of the original function. So the first graph is actually what you would draw, and if you just had f of x equal to x plus 2, then this would be the graph of the function with no domain restrictions, right? The domain here would be all real numbers, and that's really the difference between the two functions. Now, because we're only missing one point, it would be easy for us to fill in this hole by saying use this function, right, by making f of x into a piecewise function, by saying we'll use this function when it's every number but positive 2, but then when x is 2, just let it be 2. And if we were to do something like that, so let's say we said, okay, let f of x be a piecewise function, and I'm just going to take a moment to write this rational up here, right? And so use this when x is not equal to 2, but then use just the number 2 when x is equal to 2. And if we were doing something like this, we'd be able to essentially fill in this hole and change the picture from here to there, right? However, if we're looking at g of x, which is x plus 2 over x minus 3, there's really nothing we can do to fill in the hole that is being created by x minus 3 because we can't cancel anything on the numerator to get rid of this problem in the denominator. And so when you have an unremovable discontinuity, this is when you end up with a vertical asymptote. in the first case with the removable discontinuity, you just end up with a hole like we had here, right? You just end up with a hole in the graph. But for an unremovable discontinuity, you end up with these vertical dotted lines that the picture will never cross. And so this is just a quick sketch of what this function actually looks like in case you were curious. But you'll figure we're going to go through how to graph these things in the next lecture. And so we talked about the end behavior of rational functions being broken up into three different cases. So let's go ahead and talk about what the three different cases are. Okay, so the end behavior cases. So if h of x is equal to f of x over g of x, and here f of x and g of x are polynomials, so let me just go ahead and write that. F of x and g of x are polynomials. Well, so case one, if the degree of f of x, and remember that the degree of a polynomial is the power of the largest power of x in that polynomial. So if the degree of f of x is larger than the degree of g of x, then as x approaches positive and negative infinity, then y will approach positive or negative infinity. And so this tells us that there's no horizontal asymptote. And this is kind of the case of what we got with regular polynomials. So case one is kind of like the case for regular polynomials, where we had to kind of look at what was the leading term of the polynomial, what was the degree of it, and decide, you know, if it was even or odd, whether it would be going up or down. And you'll do the same thing here. Okay, well, what about case two? Well, if the degree of the function on top is less than the degree of the polynomial on bottom, then as x approaches positive and negative infinity, y will approach 0. And so what do we mean by y will approach 0? Well, it's just that as x gets to positive, really big positive, or really big negative, negative infinity, our picture is going to essentially start hugging the x-axis, because that's the value of y equals 0. Now we don't know whether it's going to be from above or below, but the idea is that eventually our pictures are going to hug the x-axis. And our third case is if the degree of f of x is the same as the degree of g of x, then as x approaches positive and negative infinity, then y will approach p over q. And so our horizontal asymptote will be equal to p over q, where p is the leading coefficient of f of x, and q is the leading coefficient of g of x. Okay? And so we have three little examples on the left-hand side here. And so you can see in this case, we have case one, right, where the degree of the polynomial on top is a 3, but the degree of the polynomial on bottom is a 1. And so since 3 is larger than 1, this is going to tell us that we have no horizontal asymptote. In the second example, you'll see that the degree of the polynomial on top is less than the degree of the polynomial on bottom. And if that's the case, then your horizontal asymptote is going to be y equals 0, right? It's going to hug the x-axis. Let me go ahead and rewrite that h. And in our third case, if the degree of the polynomial on top is the same of the degree of the polynomial on bottom, then your horizontal asymptote is essentially a ratio of the leading coefficients of these polynomials. And so because they're both x squared, the horizontal asymptote is just going to be this fraction here, the leading coefficient on top over the leading coefficient on bottom. So the horizontal asymptote for this example will be y equals 3/7. Okay? And so how do you figure out end behavior without knowing these tricks? And the answer to that question is by doing long division. And so we covered long division a section or two ago, but if you were to do that for our first polynomial, so we have 3x cubed plus 1 divided by x plus 1, and we could do long division many times x times what gives us 3x cubed, or you could think of it as how many times does x go into 3x cubed. Well, remember when we do long division that we want to fill in placeholders for all the terms that we're missing. And so the question is the same though. X goes into 3x cubed how many times? Well, it goes into it 3x squared times. Because this is a binomial, we have to FOIL 3x squared times x. Well, that's exactly what we wanted, 3x cubed. 3x squared times 1 is 3x squared. So now we subtract, and we get negative 3x squared. Okay, how many times does x go into 3x, negative 3x squared? Well, it goes into it negative 3x times. And so we get negative 3x squared minus 3x. And so now we're going to subtract, just like we've done before. And we're going to get 0 here. And we're going to get 0 minus 3x, right? 0x minus 3x is going to give us positive 3x. I'm going to bring down our 1. How many times does x go into 3x? Well, it goes into it 3 times. Excuse me. So we're going to get 3x plus 3. Then we're going to subtract, and we get negative 2, because 1 minus 3 is negative 2. So our quotient here is going to be equal to 3x squared minus 3x plus 3, remainder negative 2, which we can write as plus negative 2 over x plus 1. And so the end behavior of this polynomial, right, because we know we have no horizontal asymptote, is going to be the same end behavior of this polynomial. You don't really have to worry about the remainder here, but the idea is that because this is an even power, right, recall from our discussion about end behavior of polynomials, because the leading term here is 3x squared, that tells us as x approaches negative infinity, it's going to behave like a parabola, right? Whether it approaches positive or negative infinity, and since parabolas on both sides, y will approach positive infinity, our end behavior is going to be the same here, right? So as x approaches negative infinity, y will approach positive infinity, and as x approaches positive infinity, y will also approach positive infinity. So you can also find the end behaviors by doing this. However, knowing these tricks for case 2 and case 3 will make it so you don't actually have to do the long division in every case. All right? So we have an example set up for the next lecture, and we'll go through that one thoroughly. And I'll see you in the next video.